Are you guys getting a kind of like a rough idea of what the big O notation is talking about? It's basically saying, the amount of time is proportional to whatever is in the parentheses. Okay? Is log n better or is n better? Which one is smaller? Which one increases slower? The log of n increases slower. Very good. So now let's go ahead and take a look at something that we have not taken a look at. Let's look at sorting algorithms. Okay, because in order to use binary search, the array has to be sorted first. So it seems kind of important that we have to know, how do you sort an array? There are many ways to sort an array. The first one, or the most common one that people look at, is called a bubble sort algorithm. Bubble sort. And if you look at the bubble sort algorithm, it gives you the average case performance, which is big O of n squared. Is big O of n squared better, or is big O of n better? Big O of n is better, because big O of n squared is going to increase like this. It's not really bad, it's not exponential, but it's not as good as a linear one. Next, we want to look up another search algorithm. Let's say we want to look up merge sort. Merge. I typed, it's just being slow. So we look up merge sort. And it has a very interesting animation. This time it doesn't use the big O notation, but it's close enough. Average case performance is big O of n log n, n times log n. Which one is better? Bubble sort or merge sort? Merge sort is better. Okay? Merge sort has a time complexity that is better than bubble sort. So it's the same thing. I can work with a slower computer with merge sort, and somebody else can use bubble sort on a faster computer. Initially, for smaller test cases, yes, the other guy is going to win. At some point, I will win because the shape of my curve is different from the shape of the other curve. Do we have any questions here? No question? Yep, go ahead.
Go back on the algorithm and look up how log actually works. Do you also understand it?
Sure. Just one on this again. Okay, the way log, the math function log works is like this. I can just use a whiteboard to explain it. Okay, the log. Okay, you can always specify a base for a log. Okay, if you specify base log 2, then the log of 2 itself is 1. And that's because 2 to the power of 1 is 2. If you say log base 2 of 4, it is 2 because 2 to the power of 2 is 2. If you say log or base 2 16, it is 4 because 2 to the power of 4 is 16. It is another way to express the relationship between the base, the power, and the value that you're representing. Because you can see that 16 is the same 16 here, 4 is representing the power, and 2 is representing the base.
We get 2 to the power 2 equals 2, 2 to the power 2
Power 2 equals 4.
equals 4.
You type it on the board.
Huh?
2 to the power 2 equals
4.
2. You got it written down.
Log 2
4
of 4 equals 2. 2 to the power 2 equals not 2, it should equal 4.
Did I make a mistake somewhere? Oh, right, okay, I see. Sorry. In other words, log is a way to find the proper exponent given a base to get to a certain number.
In the equation, it don't have log. It don't get log 2. It just gets log 10.
Because it doesn't matter. The base of the log is only controlling a constant. It's only controlling like a constant. It does not really change the shape of the. Okay. What I really want to say is the log of k of a certain number is, okay, let's say this is y. Okay. if I want to take the log of another value, let's say it's m of k of x, this number is basically a certain constant times k, times y. So we're only changing a particular constant here. It doesn't change the shape of the curve. But the essence of log is it finds the proper exponent to get to a particular value. Do we have any questions about the big O notation and why it is important? No questions? But do we have any algorithms that have really, really nasty, time complexities? In other words, we look at bubble sort, which has a time complexity of big O of n squared, and we say that's not very good. Okay, it's not as good as n log n. But do we have anything that is worse than n squared? What do you think would be worse than n squared?
N to n.
N cubed would be bad. Okay, n to the power of n would also be bad. How about n factorial? N factorial is one of the worst ones. Okay, and there are algorithms with a time complexity that has a factorial component to it. Okay, so since we are talking about job security and how you can convince your boss that he should keep you, okay, let's talk about the idea of NP completeness. Okay, now this is one of those concepts that they only talk about in the upper division class in a 4-year university. But when they talk about NP completeness, they never talk about why do we care about NP completeness. Okay, unfortunately. Okay, so let's use an example. The example is this time you're writing a program to optimize how you want to deliver pizzas. Okay, so you're working for a Pizza Hut. Okay, one of those pizza chains where you have to send somebody to deliver pizzas. How many pizzas do you think a pizza delivery person will deliver in one particular trip? 200. Would any company stack up 200 piping hot pizzas and ask the delivery boy and say, "Could you deliver these 200 pizzas to these different places?"
Different places. It was all the same place.
Exactly. So in terms of number of destinations, a pizza delivery person probably has 4 or 5 to deal with for each trip, max, right? Because otherwise, by the time you get to the last stop, guess what? The pizza is not going to be very attractive, right? You have, cold, soggy pizzas, and the customer would just say, "I don't want it," and the pizza delivery person will have to take it back, and then somebody has to pay for that. Okay, so 4 or 5 stops would be good. So let's just say that you figure out how to find out, okay, these are the locations, and this is the best way to, visit all these points to optimize the path. So the pizza delivery truck can come back to the pizza place the quickest. Okay, are we okay so far with the concept? So your boss asks you to write a program to do exactly that. It is optimization, and you wrote a program. The program so happens to have the n factorial as a component of the time complexity. Why do you think that search algorithm would have a n factorial component to it? Let's think about it. And once again, it is good to have an example. Okay. Let's turn on the lights. I can use a whiteboard because this part will not be in an exam, but I do want you guys to have some exposure, just so that we understand what we are talking about here. Let's say that you only have 4 destinations. A, B, C, D are the 4 destinations. Let's also say that A, B, C, D, in terms of a Google map, they're not exactly lined up on a particular single linear line. So it's not really easy to determine, what order is the best order. In other words, this is the pizza place, and A, B, C, D appear to be pretty much at the same distance away from the pizza shop. So it is not really clear which order is really the best. You really have to look into the the time and then the traffic pattern and stuff like that to make the determination. How many different ways can I make routes here? Well, how many choices do I have to pick the first destination when I have a total of 4? I can pick any one of the 4 as my first destination. Once I'm done with the first destination, how many do I have left for my second destination? We got 3 left, and then 2, and then 1. In other words, in this case, we have 24 possible permutations. Okay, this is called a permutation because the order is important. We have 24 permutations. And I will have to figure out, okay, with A, B, C, D, it takes this much time. With A, C, B, D, it will take this much time. With A, D, B, C, it takes this much time, and so on. So in other words, I have exactly 24 routes to consider. I figure out the time for each one of these 24 routes. Whichever one has the least amount of time is the one that I would say, okay, pizza delivery person, this is the best route to cover all 4 destinations. Is that making any sense? Yep.
It's not math, that's words.
I'm pretty sure they use something smarter. As we will see that this is not going to be very good when you have a large number of destinations. So with 4 destinations is 24. With 5 destinations, it's going to be 120 possible routes. With 6 destinations, we have 720 possible routes. Okay, so that's why the time complexity of an algorithm like this is called big O of n factorial, n being the number of destinations in this case. Are we doing okay so far? Okay. So let's say you wrote an algorithm exactly like this to solve the problem. Your boss was very happy because you're saving a lot of gas money, and also the pizza delivery person gets back to the shop and help out with other duties. So in general, the shop is saving a lot of money because you're saving transit time when the person is delivering pizzas. So one day your boss came to your cubicle and said, "I'm going to fire you." But what, boss? I wrote you the very nice algorithm. You're saving gobs of money, and then your boss tells you, "Yeah, well, you seem to be saving me a lot of money, but you know what? You embarrassed me." What? I embarrassed you? Why? The boss said, "Well, your program was working so well. My buddy over at UPS or some delivery company says, well, why don't you let me run your program for my applications, right?" Okay, because when you think about UPS or FedEx, they also have a certain number of destinations to visit, to drop off the packages and whatnot, to pick up, to drop off. So if it works for pizza delivery, it should work for FedEx or UPS also. And then your boss said, "Your program just hung up. We started to run your program and it just didn't come back. It did not come back with an answer. It just chews up all the processing resources, and I was just completely embarrassed in front of my friend and his company." Okay? So you're going to be fired. Well, then you ask your boss, okay, exactly how many stops are they making for each truck? But what do you guys think? Has anyone worked for FedEx or UPS? Hundreds? Let's say it's 100. Okay, let's just say it's 100. Okay, so you're talking about 100 factorial here. Doesn't look very harmful. Doesn't look very bad. But do we know what kind of number we're talking about here? 100 factorial? It's a huge number, okay? I know this is a huge number because I used to have a Casio calculator. The old Casio calculators can only represent values up to 10 to the power of 99. That's the largest number it can represent using a scientific notation. I ran out of the range of value, not at 100, but at 16.